Okay, so we've learned how to multiply matrices. Addition, subtraction, scalar multiplication of matrices is pretty straightforward. That's just the same as in vectors, right? So if you had 5 times 2, 1, we know how to do scalar multiplication of vectors, easy, 10, 5. Likewise, if you had addition or subtraction of vectors, as long as they're the same dimension, 1, 6, and we're adding these, obviously you just add components. So that stuff is easy, 3, 7. Matrices sort of behave the same way. You can add, you can subtract, you can do scalar multiplication of matrices without a lot of grief. It's the multiplication of a matrix by a matrix, which is unusual. So we saw the 2 videos of a 2 by 2 times a 2 by 2, and then we had a 2 by 3 times a 3 by 1, and we saw how those types of multiplications come out. What this video is going to be talking about are inverses. Inverse and also identity. And this is for square matrices only. So we'll start with the 2 by 2 because that's, I guess, the least complicated case we can come up with. Let's suppose we had, I'll just make up some numbers, 3, 5, negative 1, 10. And I'm going to claim that there is an identity matrix for multiplication. I can multiply this by the matrix 1, 0, 0, 1. This will be called the identity matrix. It has 1s down the main diagonal, 0s on the minor diagonal. Actually, 0s everywhere else. And when we see a 3 by 3, you'll see there's just 1s down the main diagonal. And the claim is if you do the row column multiplication here, it doesn't change this original matrix. So if this is A and this is what I'll call I, no, not artificial intelligence, this is the identity matrix, you'll get A again. Okay, so let's see. We know that this is a 2 by 2 times a 2 by 2, pretty straightforward. Row, so there's 3 plus 0. Row, second column, there's 0 plus 5. Second row, first column, there's negative 1 plus 0. And second row, second column, 0 and 10. And sure enough, this gives us the original matrix. Now, the intriguing thing about this identity is it is one of the few cases where it doesn't matter the order of operations. So in general, matrix multiplication is not commutative. But in this case, it is. So if I put the identity on the left side here, I still get the original matrix A. In most cases, this doesn't work, but for this type of multiplication with the identity matrix, it does. So again, just a quick check, rows and columns. First row, so this is 3 plus 0. This is 5 plus 0. Second row, this is 0 minus 1. And second row, second column, 0, 10. Now, so what? Who cares? Who cares about this identity matrix? It's going to be tied closely into solving systems of equations, and that's our approach here. What we want to do is want to come up with the inverse matrix. Okay, so inverses and identities sort of go together. Think of just real numbers for a minute. If I had the number 5, what can I multiply by 5 to keep 5? And obviously that's 1, right? So this is called the multiplicative identity. Where does that come in the real number system? If I said 5, I need the multiplicative inverse to get 1, and we know that's going to be 1/5. So every real number, except for 0, has an inverse, so that when you multiply the two together, you get the identity. Sort of the same thing with matrices. If we have a matrix, again, let's just pick 5, 2, 1, 6. There's a matrix. There will be an inverse here, 5, 2, 1, 6 inverse, so that when we multiply these together, we get the identity matrix. And again, the identity matrix 1, 0, 0, 1. Okay, so that's what we're going to be shooting for. Now, how do you find this? How do you find this identity matrix? Let me give you a simple procedure for 2 by 2s, let you practice it. and then we'll do some more stuff with these identities coming up. Okay. So the first thing you want to do to find the inverse is you want to check and make sure that it is invertible. Just like in the real numbers, the number 0 has no multiplicative inverse. There's nothing you can multiply that by to get the identity. Sometimes there'll be a matrix that doesn't have a matrix inverse, an inverse. So the way you check this is you just check the determinant. So off to the side somewhere, let's go and just check out the determinant. 5, 2, 1, 6, and what's that? That's 30 minus 2 is 28. Okay, so that's not 0, which is good. We now can get an inverse. This is how you get the inverse. Okay, to find the inverse of this matrix, you are going to swap the elements on the main diagonal. So the 5 and the 6 trade places, 6 and 5. The elements on the minor diagonal, the 1 and 2, they just become negatives. They become opposites. If they were negative, they become positive. In this case, both were positive, so we make them negative. And then every one of these numbers, you're going to divide by the determinant, which was 28, 28, 28, 28, and 28. That's why it's important that this not be 0, right? Because you can't divide by 0. So I claim that this now is going to be the inverse of the original matrix. Let's double check and just see that it works. Okay, so we have 5, 2, 1, 6. I claim if you multiply this by 6 over 28, yes, I could reduce that if I wanted to. I'm going to leave it as 6 over 28, minus 2 over 28, minus 1 over 28, and then 5 over 28. The claim is if I multiply an inverse by its original, I should get the identity. Let's see that we do. Okay, so what we're expecting now is if we made all the arithmetic right, this number here should be a 1, this should be a 0, this should be a 0, and this should be a 1, right? That's what we're shooting for. Well, let's give it a shot. First row, first column. There's 30 28ths minus 2 28ths. Well, 30 minus 2 is 28 28ths. That's a 1. First row, second column. There's minus 10 28ths, and there's plus 10 28ths. That's 0. Second row, first column. There's 6 28ths. Take away 6 28ths. That's 0. And lastly, second row, second column. There's minus 2 28ths, and then plus 30 28ths. Minus 2 plus 30 is 28 28ths, which is 1. And it works. You might also want to try reversing these, because it will also work if we remember for a matrix and its inverse, it is actually commutative, unlike most cases. So if we had the 6 28ths and the minus 2 28ths and the minus 1 28th and the 5 28ths here, and we were to multiply that by the 5 2 1 6, again, we should get I. Okay, so finding the inverse of a 2 by 2 matrix. We want you to be able to do that by hand. You can do that on the calculator. If you actually put in on the calculator this matrix, call it A. A spits out to be 5, 2, 1, 6. And then you ask the calculator, what is A inverse? Just use the little -1 button like with trig inverses. It will spit out the inverse matrix. Now, it will probably be decimals, and there may be a lot of decimals there. So after you get it with all these numbers here, you might want to convert it to fractions, and then even then the fractions would be reduced down to lowest denominator. But we want you to do it by hand. Okay.